Okay, so here we go. The equation, mechanics equation sheet, part 2 now. So we had talked about impulse in the last one. So now we're starting with this one. This is about the stupidest equation that you could ever write down on a test. You never ever use it just like this. This is really two equations in one. Okay, this is really the force of friction is less than mu sub s Fn, and the force of friction is equal to mu k F sub n. So let's just remind ourselves what happens with friction. So I had started drawing this in the last one. Okay. Let's say we apply a force. So I'm pushing on a table, and I push with this many newtons, and friction pushes that much back. And doot, doot. And it does it until, boop, boop, boop. I didn't really give myself a lot of room here. We overcome static friction. And then all of a sudden, it's constant. Okay? So again, this value is mu s Fn. This value is mu k Fn. So the force of friction does whatever it needs to do until it reaches this critical point, and then it drops down and is a constant. Okay, mu s is always greater than mu k, so this works. But again, this equation as written is not anything you actually use. Okay, let's keep going. This is our ever fun concept of work being a change in energy, okay, and then relating it to the integral of f dot dr. Okay, this is not necessarily the most useful equation either. You tend to use a lot different things than just this. All right, let's talk about a few situations. If the force is constant, right, so let's say we have a box, and oh, my pen is dying. Here, I'm going to get a new piece of paper. Okay. Let's say we have, are you kidding? There we go. Let's say we have a box. I'm applying a force, and it's going through a distance, or displacement, I should say. This F parallel is the thing we care about, because when we say F dot D, we're talking about the parallel component. That's the most important part. This is for constant force, right? This is sort of the useful thing. If you have an F as a function of X, then you do need to do that, okay? So that's, that's the trick there. In general, we relate works to changes in energies. And of course, there's a way more to that than just this equation, right? So remember, when we do work, we are always talking about work on an object versus work by an object. And I'm going to have just a totally different video for that whole topic. Okay, so let's just keep going on the equation sheet. So this will be for a whole other video. This kinetic energy, 1/2 mv squared. Cool. Definition of power. So power is the rate of change of that energy or work, that energy changing or that work being done. And this is equivalence, F dot V. So this is sometimes useful. So this is when you're like, let me unit that thing up, right? If you're given a force and a velocity and you're asked for power, right? Yeah, you could probably get there with some of this other stuff, but this is what it's begging for. So it's always nice to remember that one. All right, delta U sub G. That is the change in potential energy, the gravitational potential energy. And that's mg delta H. So that's, again, if we take something and we move it up, right, we are increasing the gravitational potential energy. remember potential energy needs to, it's part of a system, right? And so the system here is this pen and the earth, right? So you can't just talk about potential energy of a thing without actually having a whole idea about a system. And when we did gravity, we had a much sort of richer feeling about that when we had, two masses. So, all right, moving on. Oh, yes, rotational stuff. Okay, this is centripetal acceleration, and the form is v squared over r. We can also talk about rotational velocity, omega squared. So this is in radians per second. And so when you get a radians squared per second squared times a meter, you do get a meter per second squared. So that works. This is for, nice uniform circular motion where whatever forces add up in the centripetal or radial direction, we get this ma, this is just Newton's second law for rotational motion, because this a is just that. Okay? Okay, torque. Remember R cross F, R perp F, or R F perp. You always want to look at, so there's your R, here's your F, that's your F perp, right? The other way to think about it is there's your R perp, okay? So this is, one of those things you just need to work on if you haven't internalized it yet. Seeing those components. Cross products give you perp components, dot products, you care about the parallel components. Okay, so I think I need to move this up now. This is Newton's second law in rotational form, right? That's angular acceleration is the net torque divided by moment of inertia. And moment of inertia is that bad boy. It's you have all the different, masses a certain radius away, and then we're wondering, how does this thing resist acceleration? Because that's a moment of inertia. It's inertia. It's the rotational equivalent to mass, which is a measure of inertia. So if it's discrete masses, you can just sum up all the m and then r squareds. Or if it's particularly mean and fun, you will have a continuous object, and then you need to do the integral of r squared dm. And remember, we did dm by introducing things like lambda, which was a mass per unit length. So you can remind yourself of those types of things. This is the position of the center of mass, and you just sum up each of those masses with each of those distances divided by the total mass. Those problems tend to be pretty straightforward. Sometimes you have to do them, one dimension at a time, but in the grand scheme of things, those are pretty straightforward. V equals r omega is your, linear velocity is the radius times the angular velocity. Another important thing here is a equals r alpha and x equals r theta. So it's always the r times the Greek letter gives you the Roman letter. Okay. So with that, you can do angular kinematics relatively easily. Okay, L equals R cross P, that is angular momentum. And so just like momentum was m times v, angular momentum is m times v, right? I times omega. It's also R cross P. Again, the cross product, you're looking for that perp, right? R perp, my bad. R perp P, or P perp R. Angular kinetic energy, these are important when you're doing whole conservation of energy problems. and you have something rolling, right? And with the rolling problems, with rolling without slipping, your velocity of your center of mass is your omega times r. And so when you do those conservation of energy problems, you have a rotational kinetic energy term and a translational kinetic energy term. And using this, you can link it so that everything comes out in the same kind of variables, and so things cancel beautifully. Okay, and the last thing here is these are the kinematic equations. Whee! Up here, they of course didn't do omega squared as omega naught squared plus 2 alpha theta minus theta naught, but of course that one works too, and this is only for alpha being constant. For the 2020 exam, this is springs. Okay, this actually might be useful. This is Hooke's law, right, where this is the force due to a spring, and that's the displacement from equilibrium. Okay, so there are ways to do it without actually doing simple harmonic motion. This is, of course, another one. Spring potential energy, 1/2 kx squared. Okay, so these two go, but these are oscillations and simple harmonic motion and gravity. So these are not on your 2020 test. Okay, thanks.